Hi everyone, this is my third video in the series of quantum chemistry classes. In this video, we shall learn about well-behaved function, eigenvalue equation, eigenvalues and eigenfunctions, their meaning and the way of identifying the eigenvalues and eigenfunctions. And at last, we shall try to solve one or two problems based on the eigenvalues and eigenfunctions that are asked in competitive examinations like IIT JAM and GATE examination. So before going to the topic, those who have not yet subscribed to my channel, please do subscribe and press the bell icon so that you will get the notifications regarding any update in the channel. And now shall directly enter into the topic. So in order to better understand the concept of eigenvalues and eigenfunction, one should have the knowledge regarding the term well-behaved function. See, if you want to call any function, say f, as a well-behaved function, that function is supposed to satisfy these three conditions. In actual sense, we used to say, if any function is to be considered an accepted function, that should satisfy these three conditions. What are those? First condition, the function should remain with finite values, means the function should have a finite value. You may get a doubt in your mind. What if the function is not having a finite value? Means if it is having infinite value, what could be the problem? The thing is, the logic behind this concept is, if a function is having infinite value at any point, that actually means the function is giving information about infinite probability of finding the particle at that particular point. That actually creates an absurdity in the view of quantum mechanical concept. See, if the function is having a finite picture, then it is possible to identify any of its properties, say for example position, momentum, thereby identifying the kinetic energy, like this. So it is better to analyze a function when it is having finite values. Okay, so that is the condition the function is supposed to satisfy in order to consider it as a well-behaved function. And the second condition is the function should be single valued. Means, as we said, the function should have a finite value and that finite value should be single valued. That means the function should have one and only one value at a particular point. It should not give more 2 or 3 values for the function at a given point. This restriction actually arises because the probability at any point is supposed to be unambiguous. There should not create any ambiguity in determining, in analyzing the function at a given point. That's why the function is supposed to have single valued. That is the second condition the function is supposed to satisfy in order to call it as a well-behaved function. And the third and the most important condition is the function and its first derivative should be continuous at all the points. See, in the space specified for the system, that is, they must not change abruptly at any point for a slight change in coordinate. Then the function and its first derivative will be considered as continuous. This condition actually comes to get a single valued as well for the finite values. These three are actually the interrelated conditions for that given function so as to consider it as a well-behaved function. So as a whole and solely we can say any function that satisfies all these three conditions will be considered as a well-behaved function. And now we shall go to the main topic, that is eigenvalues and eigenfunction. Eigenvalues and eigenfunctions. This is the most important concept in the quantum mechanics. So if you consider any well-behaved function, and if an operator is operating on this well-behaved function, obviously we have the meaning of an operator, means when it acts on a function, it's supposed to give another function. right? That is the actual meaning of an operator. But here, when an operator, say a cap, when this operator operates on a well-behaved function, it should give the same function once again. I repeat, when an operator a cap is operating on a well-behaved function f, it should give the same function provided that function should be multiplied with a constant. Then such the equation what we will get will be called as eigenvalue equation. So let me say, if a cap, an operator, if an operator a cap operates on a well-behaved function, on a well-behaved function to give same function, but multiplied with a constant. Multiplied with a constant. Then such an equation is called as eigenvalue equation. So let me write in this way. Here the operator a cap is operating on a function f of x so as to give a constant a and the same function once again f of x. So I repeat, a cap, an operator acting on a function so as to give the same function but multiplied with a constant. Then that complete equation is called as eigenvalue equation. And here in the eigenvalue equation, the constant which is multiplying with the function, that is a, this constant is actually called as eigenvalue. And the function onto which the operator is actually acting, that function is called as eigenfunction. So this is the actual meaning of eigenvalue, eigenfunction and eigenvalue equation. And here the definition I have given for the meaning of eigenvalues and eigenfunction, that means from the eigenvalue equation. Means the constant which is multiplied with the function is called as eigenvalue, which is present in the eigenvalue equation. And in the eigenvalue equation, the function on which the operator is operating is called as eigenfunction. And now we shall look over to some of the simple examples so as to understand the concept of eigenvalue equation, eigenvalue as well eigenequation. So let me consider one example. Let me consider a function f of x will be e power minus ax. This will be the function. And let me consider the operator a cap as d by dx. And this is the operator which is acting on the function f of x, whose value is e power minus x. So the operator a cap will be operating on the function f of x, so that the operator is d by dx, which is operating on the function e power minus ax. So we will be getting minus a into e to the power of minus ax. Hope you can observe. So here the operator we are operating on the function e power minus ax is d by dx, and the function is e power minus ax, which is produced once again the same function, that is e power minus ax, provided it is multiplied with a constant, that is minus a. So that this can be considered as an eigenvalue equation. Hope you understood. And here the constant multiplied with the function is a, and this is the eigenvalue, and the function on which the operator is operating in eigenvalue equation, that is d by dx, is operating on e power minus ax, and this e power minus ax is the eigenfunction. Clear? So here minus a is the eigenvalue, e power minus ax is the eigen function. And now we shall consider one more example for analyzing the eigenvalue equation. So let us consider a function f of x. Say f of x will be sine 2x. And let us perform the operator a cap. Let me consider once again d by dx. And now we shall operate the operator a cap on the function f of x, that is sine 2x. So a cap of f of x, that is d by dx of sine 2x. So when you perform d by dx on the sine 2x, we will be getting 2 cos 2x. So when operator is performed on a function, we are getting one more function multiplied with a constant. But this cannot be called as an eigenvalue equation. The reason is, we said the definition, the operator when it performed or operated on a function, we are supposed to get the same function and that should be multiplied with a constant. And here the function on which the operator is operated is sine 2x. And here in the derivative we are not having sine 2x. Instead we are having cos 2x. So this and this is not the same, though it is multiplying with a constant. So this is not an eigenvalue equation. So that sine 2x is not the eigenfunction of the operator d by dx. So this is the way how we can find out whether a function can be considered as an eigenvalue function or not. Suppose if I consider f of x is equals to sine 2x once again. A function is sine 2x once again, and if the operator a cap is d square by dx square. If the operator is d square by dx square, shall perform d by dx, that is a cap of f of x. A cap of f of x, that is d square by dx square of sine 2x. So means we should perform the d by dx for 2 times. So we can write this as d by dx into d by dx of sine 2x. Right. So here we know that d by dx of sine 2x will be 2 cos 2x. And again we should perform d by dx once again on this particular thing. So d by dx of 2 cos x will be minus 4 sine 2x. This is actually the derivative of d square by dx square of sine 2x. So this is a function and this is the operator. We got a derivative. I mean one more function wherein the function is once again sine 2x and is multiplied with a constant minus 4. And now we can call this as an eigenvalue equation. Hope you understood how to find out the eigenvalue equation. And here we can say sine 2x is a function. So the eigenfunction in this eigenvalue equation is sine 2x. And which is the eigenvalue then? So in order to find out the eigenvalue, we should go with the right hand part. Here the function is sine 2x, which is multiplied with minus 4, and that is actually the eigenvalue. Right? So in this way, we can easily identify the eigenvalue equation, eigenvalue, and eigenfunction. And in the quantum mechanics, the presence of eigenvalue equation can be identified in the Schrödinger wave equation also, and that we shall see as what we can say, the Schrödinger wave equation as an eigenvalue equation. Schrödinger equation as an eigenvalue equation. And we know that the Schrodinger wave equation is minus h cross square by 2m minus h cross square by 2m del square plus v of xi is equals to E psi. This is the simplified form of Schrodinger wave equation, right? And we know that in the previous video we said minus h cross square by 2m into del square plus v is actually written as h cap, which is an operator actually, which is acting on a function xi, and that will gives E psi. And now you can observe carefully, h cap psi is equals to E psi. Here the function is xi and the operator is h cap. So h cap is operating on the xi. We know that h cap is Hamiltonian operator, right? So h cap is operating on xi so as to give the function xi once again, but multiplied with the constant E, so that it completely satisfying all the conditions of eigenvalue equation. So we can call this as eigenvalue equation. And here in this Schrodinger wave equation, we can say h cap is the operator operating on the function xi, so that we got the function xi once again multiplied with the constant E, so that xi is the eigen function and E is the eigenvalue over here, right? And that's the discussion pertaining to eigenvalue function and eigenvalues based on the knowledge of well-behaved function. And now we shall see one problem which is asked in GATE examination in the year of 2013. And the question is like this, which is asked in GATE 2013 examination. And the question is, the eigenvalue of the function e power minus 2x square of the operator. They have given operator also, that is d square by dx square minus the value given is d square by dx square minus 16x square is. This is a question asked in GATE 2013 examination, and the options given are plus 4 is the first option, minus 4 is the second option, minus 1 is the third option, and plus 2 is the fourth option. And this is the question asked in GATE 2013 examination for 4 marks actually. And now we shall see which is the actual eigenvalue of this particular function on which the operator operating is d square by dx square minus 16x square. And so here the operator a cap is operating on the function f of x, that is d square by dx square minus 16x square is operating on e power minus 2x square. So now we shall solve d square by dx square minus 16x square is the operator which is acting on the function e power minus 2x square. So we can multiply this d square by dx square of e power minus 2x square minus 16x square into e power minus 2x square. And here we have the two things, d square by dx square. So we can write it like this, d by dx of e power minus 2x square minus 16x square into e power minus 2x square. And here the value of d by dx of e power minus 2x square is minus 4 e power minus 2x square. That is the derivative of d by dx of e power minus 2x square minus 16x square into e power minus 2x square. Again we have to do this one, right? So sorry, again we have to derive or get the derivative of this 2x square, right? So that will give minus 4x, or else let me write in this way, e power minus 2x square into minus 4x, right? And here once again we have to perform the derivative, differentiation of this particular thing, but here we have two terms, d by dx of e power minus 2x square into minus 4x, right? So first we should take in this way, minus 4x into d by dx of e power minus 2x square plus e power minus 2x square into d by dx of minus 4x minus 16x square into e power minus 2x square. So thus it will give minus 4x, d by dx of e power minus 2x square will be once again e power minus 2x square into minus 4x plus e power minus 2x square will remain as it is, d by dx of minus 4x will be minus 4 minus 16x square into e power minus 2x square. So here you can multiply minus into minus plus 4x into 4x, 4 4s are 16, x square will come into e power minus 2x square, and here we have plus into minus, minus 4 e power minus 2x square minus 16x square into e power minus 2x square. So plus 16x square into e power minus 2x square minus 16x square into e power minus 2x square will get cancelled, and we remain with minus 4 e power minus 2x square. This is the final value for which we got the answer. And we have the function, that is d square by dx square minus 16x square of e power minus 2x square. This is the function we actually taken on which this operator is operated, right? So we got the same function once again, but multiplied with the constant minus 4. So satisfying the condition of the eigenvalue equation. So here the eigenvalue is minus 4, which is option B. Like this, the questions will be framed in the competitive examinations like GATE and JAM examination. Thank you.